Ladies and gentlemen, welcome to the keynote session number 3. Yes, before our closing ceremony, we have another 2 exciting presentations, one from Europe and one from hosting country China. Then let me introduce our first keynote speakers. Professor Jean-Michel Torrenti. He is very active in FRB community. That's why I often see him in the meeting, especially model code. Yes, Michel is the director of the Materials and Structure Department of the IFSTTAR, France. He is also professor of this is French pronunciation, École Nationale des Ponts Chaussées. I don't know. Thank you. Jean-Michel Torrenti's research concerns mechanics of concrete and its coupling with the durability aspect, behavior of concrete at early age, creep, leaching, and it's applied to model the behavior of concrete structures such as bridges, nuclear power plants, and the nuclear waste storage. He is co-author of the various papers and books concerning, of course, concrete and concrete structures. And today he is present on concrete and climate change. How can we solve the problem? This is a big issue. Floor is yours. Michel, please.
Thank you, Mr. Chairman. I am very happy to have the opportunity to give a keynote in this conference, and I want to thank the organizers to give me this opportunity. Of course, it's a pity we cannot come to Shanghai, but because I know you worked hard to prepare the conference, but we will do our best to have nevertheless an interesting conference. My presentation is on concrete and climate change and how can we solve the problem. And I think it's important to speak of this in a FIB conference because it is not only a problem for the cement industry, it's a problem for all the concrete industry, including FIB, in fact. And so I will present some possibilities. It's more a review than my work, and I will try to quote all the authors I will use in the presentation. Of course, the first point is that, of course, thanks to Greta Thunberg, you know flight shaming. But in fact, airplane industry is only the source of 3 to 4% of the CO2 emissions in the world. And it's less than concrete, in fact. And that's why we could see in some websites or journals these titles. I like this one on the left, concrete, the most destructive material on Earth. And it's time to end your dirty concrete addiction. And the cement industry produces more CO2 emissions than most countries. It may not survive. So in fact, we of course, I think it's time to do something about the problem concerning CO2 emissions in concrete, because concrete shaming is coming, in fact. And of course, we know we have some facts. We know that the level of CO2 in the atmosphere is increasing. This is a measurement at the Mauna Loa Observatory in Hawaii, and you could see that, of course, there are annual variations, but the mean value is steadily increasing. And because here I have the last measurement, and the effect of the COVID crisis is not visible on this curve, in fact. So it's an increase that will continue for several years. And the problem is that we have some effects on nature. Here I have chosen a first example, very important for the French people. It's the question of wine. And you see the evolution of the harvest date. It's a 10-year average since the beginning of the previous century. And you see that in the last 30 years, let's say, the harvest date is sooner and sooner. And this year it was worse because, for instance, in Alsace, which is the blue curve here, in Alsace, this year it was the 3rd of September, which is here, the point here. So you see that we have a very earlier harvest. And also there is a problem of the increase of the degree of alcohol of the wine. But of course, it's something we can measure very easily in France because it is well documented, the harvest date. But we have, of course, more destructive effects. At the beginning of October this year in France and in Italy, there was the storm Alex. And for instance, in this little town in the Alps, there was more than 500 millimeters of rain in 24 hours. And it's a narrow valley, so that's why there was a lot of destruction in the valley. And the cost, we know, will be around 2 billion of euros. A lot of roads were destroyed, bridges, houses, water supply network, etc. So, and of course, in France and in Italy, some people were killed also. Of course, it's not only in Europe. Actually, we have in Vietnam also large floods. And you see with a lot of people dead and a lot of destruction also. Here, this is a view in Hue, and you could see that we could not see the bridge. Normally, there is a bridge on the river, but it's under the water. And a new typhoon is coming actually in Vietnam. So we have a lot of accumulation, and this is due, of course. We know that the increase in these events is due to the climate change. And the effect and the risk of on the economy of the climate change is well documented. And for instance, the World Economic Forum, in fact, the Davos Forum, they have a map where they place the probability of occurrence, the likelihood, and the impact. And you could see that on the right part of the top right part of the map, you have this green dots corresponding to the effect of climate change. And you could see that all the effects of climate change have a high probability of occurrence and a high impact. And compared to infectious disease, we have an example this year of infectious disease, unfortunately. And you could see that the impact, which is very important in the world economy, we have the same impact and with a larger probability of occurrence for this climate change. That's why we know that we have to do something. On the other hand, we have urbanization that will continue. Actually, 1.5 million people join cities per week. And the projection here, we have still an increase during the next 30 years. So we need to build, of course, houses, roads, water supply network, etc., for these people coming in the cities. And as an example, because we were not able to come to Shanghai, I show you an example of the evolution of Shanghai between 1987 and 2013, and you could see the large evolution and the amount of materials you need to build all this building. And I think some of the buildings are missing now. There are more buildings in Shanghai. And unfortunately, we are not there to see this. So the impact of the construction sector is very important, and it's around 40% of energy and carbon dioxide emissions, and around 11% of this are coming from the building materials: steel, cement, glass, mainly. So the materials are an important part of these emissions. And in buildings, in fact, actually, thanks to thermal regulation, the part of operational carbon you need to heat the house and heat the water, etc., is decreasing. But you could see that the embodied part is becoming larger. This is a work published last year by Rock and Al, and you could see that the operational carbon is in blue here. It's decreasing with new buildings, and the part of materials, the embodied carbon here, is increasing. So if you look at the ratio between this pink and this blue part, you could see that we are next to close to 50% now. So it means that the embodied part, the part related to the materials, is becoming larger now. And it's because, of course, we use more materials in order to reduce the operational carbon. So we have to work on this material. I have a good news. Your role matters. Firstly, on your personal life. Of course, there are several options to reduce your carbon footprint, but also when you work on the concrete industry. I have here this example of this building. Okay, it's a very large building in the La Défense, Paris area. And if you assume a service life of 50 years and these 600 kilograms of CO2 per square meter for the embodied carbon, the weight of this building is around 200,000 tons of CO2. And if you save 1% of this, you save 2,000 tons of CO2, which is very large compared to what you could do in your personal life, in fact. So we have, and of course, on the contrary, if you increase by 1%, it's very, of course, it's very important. So we have a role to play here in order to save CO2 in construction. If we look, of course, all the materials are concerned, but if we look at concrete, and if we look at a concrete made with Portland cement, of course, the cement represents 98% of the CO2 impact. It's a main part of the CO2 impact. And that's why cement represents between, let's say, 5 to 7%, depending on how you look at that, on the total CO2 emission. And if the cement industry were a country, it would be the third largest CO2 emitter. Of course, it means that the cement and concrete industry should reduce its emissions. And it's mandatory because, firstly, of the climate urgency. We have discussed of the effect on climate and the pressure of the society that will not accept that we are not doing something. But also, of course, also of the shareholders. Here you have the evolution of the market capitalization. And here you have the top 30 companies that increase carbon emissions and the top 30 companies that reduce carbon emissions. And you could see that we have a large difference now compared to the past. It means that it's better if you are a shareholder to have shares of companies that reduce carbon emissions. And of course, that's why this in October or so, in The Guardian, there was a paper of top asset owners that also want to cut big carbon emissions. They want to invest in companies that cut carbon emissions. So it's a very important point. And in Europe also we have taxes for CO2. We have what we call the ETS, the emissions trading system. We have for the industries that are emitting CO2, actually we have free quotas. It means they are allowed to emit CO2, but the free quotas are decreasing. And we know that over the next 15 years, we will have, they will disappear, these free quotas. It means that when you emit 1 ton of CO2, you have to pay for that. Actually, we have free quotas, and the level of the CO2 price is around 25 euros per ton. And we can expect that when the companies will have to buy for CO2, this price will increase. Let's say if the price is 50 euros per ton, for 1 ton of clinker, you emit around 800 kilograms of CO2. It means that you have to pay 40 euros per ton of clinker, which is very, very important. Actually, 1 ton of clinker is around, let's say, 100 euros. So it means a 40% increase of the price of the clinker. So it's very, very a big incentive for the cement companies to reduce the CO2 emissions. And that's why we have the European Cement Association, which has a policy in line with the European Commission, where the objective is to be carbon neutral by 2050. And they have what they call the 5 C's strategy. And I will decline this strategy for clinker, cement, concrete, construction, and carbonation. And they plan, for instance, to reduce within the 10 next years the CO2 emission to less than 500 kilograms of CO2 per ton of cement. Which is an increase, because here you have the world mean of the CO2 emission per ton of cement. And you could see that we are around 600 kilograms of CO2 per ton of cement, and it's more or less a constant since 10 years. So we have large efforts to do to obtain less than 500, which is here. Of course, they can work on energy efficiency of the kiln in the cement factory. In France, they plan to use biomass waste to generate heat in the kiln. And the objective is to have 50% of the heat generated by biomass in 5 years. And also more prospective research are on the reduction of the temperature in the kiln to obtain, for instance, balytic cements. And also we can have a post-treatment, and this is energetically modified cement to reduce the energy used in the kiln. Of course, we know that we can use additions, but additions, we have some limitations. Here I present the case of slag. Of course, we should use all the available blast furnace slag in concrete, but you could see that concerning blast furnace slag, almost 100% of the blast furnace slag is recovered, and 80%, almost 80% is already used in cement. So we can just, let's say, divert 21% from road to concrete, but that's not a very large. That's not a very large quantity. And second point is the fact that we should have coherent environmental product declarations, because for concrete, slag is a waste. It means that the emissions are close to zero. And for steel, it's a co-product, and they deduce, in fact, in the CO2 emission of steel, they deduce 900 kilograms of CO2 per ton of slag, which is used in cement, and that is the main part of the slag. And it means that if you add concrete and steel, something is missing, because in concrete we consider slag is zero emission, and in steel they consider it's a negative emission. So of course this situation is not correct, and it should evolve. And it should evolve, and it means that, of course, in this case, slag will be less interesting on the environmental point of view. Nevertheless, it will be interesting, nevertheless, but less interesting. We have new cement types in Europe. We will have CEM2C, meaning that we have only 50% of clinker, and another component, mainly limestone, for instance. We expect to have a CEM6 cement, ternary cement, with less than 50% of clinker, and with blast furnace slag and fly ash or limestone. Of course, you know, there are a lot of research on LC3, limestone calcinated clay cement. This is, I think this is very important because of the availability of limestone and clay on Earth. And we know that the other additions like slag, I already have discussed this point, but fly ash, for instance, also, if we want to diminish CO2 emissions, we will have to limit the use of coal for production of energy. So we need other additions, and clay, we have a lot of clay on Earth, so that's a very interesting possibility. And of course, there are also alternative cements, alkali activated materials, using locally available raw materials. You could see, for instance, John Provis papers on this subject. That was for cement. On concrete, firstly, we have to optimize the mix design with the granular stacking in particular, and the use of admixtures to reduce the quantity of paste for a given workability. And also something which is less discussed, we have to reduce margins, the overdosages. Here you have the dosage in the production of concrete for a precast plant, and you could see the required dosage was there, here. And in fact, they prepare concrete with a larger amount of cement. From, let's say, 0 to 20 kilograms of cement per cubic meter, more than was required. So it's a way, of course, in the precast plant to be on the safe side, but if you are on the safe side, you are an overdosage, in fact. We, of course, we want to use just the necessary cement, so to prescribe the right concrete for an exposure class. And also we can improve the performance-based approach rather than a prescriptive approach. For instance, in Europe, if you are near the sea, you have a requirement of 350 kilograms of binder per cubic meter, and maybe you don't need that. And of course, you need also the trained workers that are aware of the problem of CO2 also. In construction, again, do not over-design. Take into account the environmental aspect in the design, the eco-constructions, and codes like, of course, Eurocode 2 or the model code must, of course, ensure the mechanical safety, the durability, and the sustainability, which is now well visible in the new FIB policy. And again, the importance of the training of design office engineers, because they have to be aware that they can play a role to reduce the CO2 emissions in what they build. We have to look at the indicator. What is a correct indicator for concrete? For the impact is kilogram of CO2 per cubic meter. And for instance, in France, we have an example of the technical specification for low carbon concrete for the buildings of the Olympic Games in Paris. And they ask for when the strength was lower than 30 megapascal to have less than 150 kilograms of CO2 per cubic meter. And for when the strength was larger than 30 megapascal to have a 35 reduction of the impact compared to a concrete with same one. 150, here I place several mixed design and I have evaluate the CO2 impact. You see it's very low and only some of the concretes are able to obtain this result. So it's not easy to obtain this level. And also there are of course, some problems due to the evolution of the strength in time. And so there is an impact on the way you build what you want to build. And also, it's not obvious that to have the lower CO2 emission per cubic meter is the best solution. Of course, if I go back here, you see that the trend is when you increase the strength, you have an increase of the CO2 per cubic meter. Of course, if you consider a given strength, you could have very large differences, but nevertheless, there is a trend. So if you have the design of a column, it was a study made by a student at École des Ponts, El Nani, and for this building, which is also in La Défense, and he has considered a column at the bottom of the building. And he has shown in his work that considering CO2, it's better to have the minimal reinforcement. And with one type of cement it is better to have the largest strength. For instance, if the concrete uses same one cement, you could see that when you increase the strength, you have a lower amount of CO2 for a given column. And it's the same with the SEM2. Of course, with SEM3, considering slag with no impact, you have a lower value. And we are not able to obtain very easily high strength concrete with slag. Of course, I know it's possible, but it was not considered here in the study. So in fact, for instance, if you use SEM1 or SEM2, it's better to have a higher strength concrete. It means that it's better to have a concrete which has a larger CO2 per cubic meter, and you have to consider the column, or you have to consider the building. And also the design of the building was not optimized in order to minimize the impact. It was done for a classical concrete. So we have also to think about the design and improve the design. Recycling also is a possibility. Here it's an example of a site where we are involved in near Paris. And we see it was an engineer school, and it was destroyed, and all the concrete was recycled on site. And in this case, of course, it's very interesting because you avoid transportation of the demolished concrete, you avoid transportation of natural aggregates, etc. But we know also that if we don't have a high quality recycled aggregate, we have to increase the cement content. Here it's a study of Amor Benfrage and Mrs. Idir from Cerema, and they have compensate the use of a larger amount of recycled aggregates, which are low quality recycled aggregates. It means there are a lot of wood, plastics, bituminous materials, not only concrete aggregate. And you see that you have to increase the cement content to obtain a given strength. When you have 100% of aggregate, of course, a lower amount if you have 50%. But even if you have only 20% of recycled aggregates, you have to increase slightly the amount of cement. Of course, it's different when you have better aggregates. So the curve here corresponds to the concrete with the low quality aggregates. This curve corresponds here in black to high quality aggregates. And here you have the CO2 impact of 1 cubic meter of concrete with a natural aggregate transported from 22 kilometers. And here transported to 250 kilometers. And this line is going from this level to the other one with the impact of transportation. So in red, it's for natural aggregates, and the black lines are for recycled aggregates. Sorry. And you see, of course, that there is a big influence of the distance, and that if the natural aggregates are coming from more than 50 kilometers, it's better to use recycled aggregates in this case. So the conclusion, of course, it's in the case of good quality aggregate. So there are two conclusions. The first one is it's, of course, very important, the sorting of recycled aggregates. You have to eliminate all the other materials from your concrete recycled aggregates. And that's, in this case, it's better. And the second point is the importance of the transportation. Of course, if you have, like in this case, the recycled aggregates are already on site, it is, of course, interesting to use recycled aggregate. If you have a lot of transportation, of course, it will be discussed. We have also to think about reuse and design for disassembly, because, of course, when you are doing recycling, you have to demolish, to crush the concrete. And finally, you have to add again cement to obtain again concrete. And maybe we can think, okay, I have this structure. I can, let's say, dismantle here, and we can keep the beam and use it again. But of course, in this case, you have to imagine the reinforcement in order to be able to remove these parts and to keep the beam intact. Of course, this is very connected to beam for the storage and traceability of the data concerning the reused elements, and also for the conception with reuse of concrete elements. So I think there are some research actually in France and in the world about this, because of course it would certainly be better to reuse directly elements than to crush all the concrete and to recycle concrete aggregates. If we look at the CO2 impact of cement, it's mandatory, in fact, to use carbon capture at the kiln, because all the solutions I have presented will not be enough to obtain a net zero emission. And actually the evaluation is that we need to capture around 60% of the CO2 from the cement factories. And we have some examples of this technology. We have a Longship project in Norway, where they plan to capture CO2 in a cement factory and also in a waste factory. And they will transport the liquefied CO2 to in the North Sea to store it in a depleted oil well. And in Colorado, I have seen also that there will be also a project to capture carbon dioxide on a commercial scale. There are also projects to burn oxygen at the cement factories. And the only interest to burn oxygen instead of air is to obtain pure CO2 at the kiln. And the big problem here is the cost of CCS, because it will be very large. It will be a very large cost. Carbonation is the last part I want to discuss. Of course, we know that concrete carbonates, and we have we need to have a correct evaluation of natural carbonation. There was recently a publication by GUO showing that around 50% of the CO2 emitted has been captured by mortar and concrete structures. Here you have the emission, and here you have the uptake, and you see that we are around 50%. But of course, it is fair to evaluate correctly the natural carbonation, but there is no effect on climate change, because this phenomenon is already there. It exists. So there is no effect if you say concrete has stored 50% of the emitted CO2, okay, but there is no effect on climate change, unfortunately. We are also working in France on on accelerated carbonation in the project that is called FastCarb. We use recycled concrete aggregates. So we plan to have preservation of natural resources on natural aggregates, and the improvement of these recycled concrete aggregates by carbonation, and also to store CO2 in the recycled concrete aggregates. We have a PhD that will be finished this year, And Marie has studied a lot of parameters: CO2 concentration, the size of the aggregate, the water content, temperature, the natural carbonation. And here you see that the effect of water content, it's like in natural carbonation, there is an optimum for the water content. And also here you see the effect of natural carbonation. For instance, we sprayed phenolphthalein on the aggregates. You could see that here they are not carbonated, while here they are already carbonated. And there is, of course, a big difference because this one is this here, and this one is this here. So you see, of course, the importance of the natural carbonation on the uptake we can obtain by accelerated carbonation. A very interesting thing is that we obtain a decrease of the water absorption coefficient, which this high water absorption coefficient is why we need more cement when we use recycled concrete aggregate. So we can expect to save a part of the cement increase with our carbonated recycled concrete aggregates. We have actually two devices near a cement factory. Here in a cement factory owned by Vica, and this one by LafargeHolcim, and they will produce 50 tons of carbonated aggregates to prepare concrete and to verify the mechanical and durability performances. And we are also looking at the life cycle analysis and an economical evaluation of the process in the framework of this project. I think it's time to conclude now. I think, I hope you are convinced that climate change is real and that human activities are the main cause for this climate change. We need to reduce the CO2 emissions. For instance, the European Union aims to be climate neutral by 2050. I've seen China is the same, Japan is the same. And an economy with, we expect to have an economy with net zero greenhouse gas emissions. And the concrete construction sector and concrete industry should contribute to these objectives. It means that all the stakeholders, including FIB, of course, should be involved, not only the cement company. And also we need to add all the possible ways to reach this goal, because there is not only a unique solution that will solve everything. Thank you for your attention.
Thank you, Michel. Very interesting topic. Yes, I think we have a few minutes for Q&A session. Then I think we received the 3 questions. I may read those questions. 2 are from the Paulo Negro. He was also keynote lecturer yesterday. The first question is that there are other emissions than the CO2 which contribute to the global warming. For this reason, equivalent CO2 is typically considered. Cement and concrete production correspond to huge CO2 emission. How about other greenhouse gases? This is first question.
Well, I'm not sure I understand completely the question. If the question is, do we have other emissions than CO2? Of course, there are other gases, but the quantity is very low in the process. So if you mean we have to compare CO2 with other greenhouse gases, of course, concrete is only a part of finally a small part of the CO2 emission in the world, sure. But I'm not sure I answer very well to the question, because I'm not sure I understand it.
Yeah, I also have much knowledge on the other greenhouse gas from the concrete related industry. Okay, but anyway, also from second question from Paulo, the unitary price of CO2 is an effective incentive to reduce the emission in all industrial processes, including construction. Which institution or normative body should, in your opinion, be in charge of the responsibility of the setting such price?
Here, I think we can have two answers. First is what I have presented, the ETS system in Europe, the taxes on the CO2 emissions for the production of cement, but it's the same for steel, it's the same for glass, and the same for lime, etc. In this case, it's in Europe, it's a European Commission that is in charge of this system, and it is very incentive for the materials companies. And there are another answer, which is concerning buildings, for instance. Actually, we have only thermal regulations, for instance, in France. It means when you build something, you have to limit the quantity of energy you use to heat the building, let's say. But now we are introducing a new regulation, of course, always with the energy limit, but also with carbon limit. So when you build something now in France, you have to limit also the carbon emission of your building. So there are two levels on the European system for materials, and for construction is more national regulation.
Okay, then third question is, our industry is constrained to some extent by the need to follow the code and standards, which can provide a barrier or at least slow down the adoption of innovations. Do you have any comments on this point?
Sure, I have two comments. The first one is, I think that we have to convince all the people involved in the codes that it is very important to limit also the emissions due to construction, and not only to look at the mechanical behavior, for instance, durability, etc., but also to sustainability, of course. That's the first point. And the second point, of course, if you come with a new concrete, with, let's say, a low carbon concrete, and with products that are not covered by standards, of course, you have to, let's say, to do some tests in order to prove the mechanical behaviors, the durability, etc. And we have, I can speak of France, of course, only. We have in France possibilities to use, for instance, a concrete which is not covered by standards, but of course you have to perform tests in order to prove it is possible to use without large risk this concrete.
Okay, thank you. Yes, we still have one more question, but please, Michel, you can respond to this question to the Q&A box, please. So I think we move to the second keynote
Okay.
speakers. Thank you, Michel, once again.